Okay, good afternoon everybody, and welcome to the next session on audio quality. So today we want to talk about psychoacoustic models. So you already heard about some principles of hearing, psychoacoustics, but now we actually have to build a model that can actually control our coder to take advantage of these effects. So this is again our basic model of our coder, and you see the psychoacoustic model here is in this side branch. So this model then takes the signal, or audio signal, computes the sensitivities of the ear, and using this controls the quantization step size in the different subbands from our filter bank. So this is now the step where filter bank and properties of hearing come together in order to control the coder such that we have quantization noise which is inaudible. So we want to maximize the amount of quantization noise because that minimizes the bit rate. At the same time, we want to keep this quantization noise inaudible. And for that, we have to hide this quantization noise in places where the ear cannot hear it. Right? The lower the bit rate, the more quantization distortion we have. So we have to find places where to put this quantization distortion. Yeah, and this is what our models do. So for our models, we need to take a look at the properties of hearing. And the first principle is to look at the basilar membrane, the inner ear, as a filter bank. So here you can see it. This is like a simplified diagram of the inner ear. So this is basically straightened out of the inner ear. And you can see that different parts of the cochlea resonate for different frequencies. So you can think about different places on the cochlea being different bandpass filters with their own characteristics. So we have a filter bank which does something similar, but not exactly with the same type of filters. Right? So the ear actually has highly overlapping bandpass filters, and the magnitude responses are non-symmetric, asymmetric, and non-linear, level dependent. So somewhat different from our filter banks that we use. And they are non-uniform in bandwidth. The bandwidth increases with increasing frequency. So that's also different from our filter banks. For instance, the MBCT or the PQMF. These are uniform filter banks, which means the bandwidth of our bandpass filters is the same no matter where in frequency we are. For the ear, it's different. When we have higher center frequencies, the bandwidth increases. So it's not exactly the same. For our filter bank, it's not so critical, but for our psychoacoustic model, we need to take care of these differences. So the first step is to look at the threshold required of hearing. For that, you can test different people, different persons. And here in this diagram, you see the hearing threshold of 100 different people. So for 100 different people, they were asked, can you hear this tone or not? Right? And for each frequency, they found a level at which the people could hear the tone. And each has slightly different ears with slightly different sensitivities. So that's why we then compute this statistic here. The solid line is the median. So this is basically the threshold where 50% of the people are below and 50% are above this threshold. And then you can see those dashed lines. The upper dashed line means that 90% of the people have better hearing than this, but 10% worse. And similar here for this 10% line, it shows that only 10% of people had better hearing and 90% worse. So this gives you an impression of the variation of the threshold required. So this should be familiar to you from psychoacoustics lecture. So what's important for us for modeling is that we can put or approximate this solid line by a formula. Right? After all, we need to compute it in our encoder. So it's very useful to put it into an equation, into this formula. This is found to look quite similar to this solid line. So there's actually not too much to understand here in this formula, it's just an approximation. So this function looks very similar to this solid line here. And you can put it in a line in Python, for instance, and compute it. So that makes it very practical. Yeah, so here the unit, here you have the level in dB. So here vertically you have this dB axis. Then you have frequencies in kilohertz. Yeah, and that's pretty much it. Then you have the formula where you put in frequency in kilohertz and you get the threshold in dB. Yeah, and another important observation is this non-uniformity of our bandwidth. And this non-uniformity is reflected in this so-called critical bands and the Barbed scale. Right? So this Barbed scale has a non-uniform distribution, just like the figures in our ear. So this is not exactly the bandwidth of the figures in our ear, but they grow with the same tendency. Right? You have the same increase in bandwidth or increasing frequency as for the ear. And here you can see for the low bands, 0, 1, 2, you have an increase in bandwidth of, or you have the bandwidth of 100 Hertz. Right? So each band is 100 Hertz. But then when you come to higher Barbed bands, like 23 and 24, here you can see that the bandwidth is 3.5 kilohertz. Can you see that? So that means the bandwidth is growing a lot. So here you can see the 100 Hertz goes up to about Barbed number 5. So there we have already 510 Hertz. Then 6 we have the frequency boundary 630. So it's already growing by 120 and so on. So this bandwidth is becoming bigger and bigger. And this is basically like the ear behaves in the increase in bandwidth of the cochlear figures. Yeah. So the scale is ranging from 0 to 20 to 24, where we have 50,500 Hertz. So why is this ending at 24? What do you think? Huh?
It should be pretty low.
Well, it's not, right? So why is this ending at 24?
Probably 25 is bigger than 20 kilohertz, so they just didn't accept.
Yeah, why?
Because it's more than the person can hear.
Because humans here cannot distinguish between 18s and no, it can distinguish between 80s and 90s here, but in between doesn't.
Well, actually, we can distinguish between different frequencies, but the problem is the sensitivity. Right? So when you go back at this image here, so look what happens at 20 kilohertz. Right? 20 kilohertz, basically nobody can hear anymore.
Yeah.
Right? So you can see here the dash line. If you extend the dash line, maybe the best 10% can hear a little bit of it when you have it very loud. But usually, like the 50% curve, basically nobody can hear it. So here, you can see here in the middle, you have something like 13 kilohertz. So in the range between 13 and 15 kilohertz is basically over. Right? So most people become very insensitive above 15 or 16 kilohertz. And that's reflected in the Barbed scale. Right? That's why the Barbed scale ends around here, where this line goes up very, very steeply. So when this line goes up very steeply, that means going up a little bit in frequency means the sensitivity decreases a lot. Right? So that's why usually you say the upper limit of hearing is 16 kilohertz.
24.
You mean the Barbed number?
Yeah.
Yeah, right. So this is basically the upper limit. So 20 kilohertz is maybe infants, but grown-ups have a limit of maybe 16 kilohertz or below, depending on age. Right. And here we're dealing with the average hearing. So going up to about 16 kilohertz is sufficient.
Could you please explain the other columns, the left three?
Yeah, good point. So here, this is the Barbed number in the first column. FU means lower end of the frequency of the band, and this is FO means over, U means unter, so lower, O means over, so upper. It comes because this is from this German book about hearing, Zwicker. So that's why I have those German acronyms here. So this is the lower band edge, upper band edge, and this is the center, the bandwidth, and this is the center. So FM like middle, so this is the center of the band, and this is the delta means the bandwidth of each band.
The first one is the lowest one, yeah?
Yeah, so number 0 goes from frequency 0 up to 100 hertz, which means we have 100 hertz bandwidth, and the center is 50 hertz. The next band goes from 100 to 200 hertz. Again, we have a bandwidth of 100, and we have the center frequency of 150. Make sense?
Makes sense.
And here you can also see how the bandwidth goes up after around 500 hertz. So here it's becoming bigger and bigger until it reaches about 3.5 kilohertz down here. Right. Yeah, I added a 0 here because this is supposed to be 12,000. Yeah, so the relation between the Barbed unit, which we call Z, here, Z in Barbed, and we can also add that here. Z scale. So the Z scale is the Barbed scale, and you need a relationship between Z and frequency F, between Barbed and frequency in kilohertz. And similar to what we just saw for approximating the threshold required, now we need a formula to map between frequency and Barbed, to basically be able to simulate those non-uniform bandwidths of the ear. Yeah, and this is what we see here. So the critical band concept is used in many models and hypotheses. The unit was defined leading to the so-called critical band with its scale, which ranges from 0 to 24. And 1 bar corresponds to 1 so-called critical band. And here are the approximations. So they're actually different approximations. And this is one of the approximations, Z in Barbed, and then you have this formula, and here you plug in F in kilohertz using the arc tangents. And then you can go back, let's see, oh yeah, this is the bandwidth, the coding bandwidth. So here you have the formula for the bandwidth, and here you have a formula for the center frequencies of each of those bands. Make sense? So here's the mapping, frequency to Barbed, and the law formula is frequency to bandwidth of a Barbed subband. Yeah, often we need a so-called tonality, because the ear treats tonal sounds, tonal audio signals, like a tone from the flute, differently than noises or narrowband noises like hissing sounds like S. And for this we can define a tonality index, which is 0 for a noisy signal and 1 for a totally tonal signal. And in system theory, sharp spectral lines means we have a periodic signal, and that's tonal. Right? And that also means it's predictable. So if the signal is predictable, then it should be periodic. If you can perfectly predict it, that means you have some sort of periodicity. So therefore, we can use prediction to approximate if a signal is tonal or not. Yeah, here's a formula for computing the predictability. So this is basically the prediction game that we compute. If we have a predictor, so let's see, R is the prediction residual. Do we actually know what a prediction residual is? We didn't have it so far, right? Do you know? Okay. Yeah, so then just take it as coming out of some predictor, right? So far black box. We'll still come to it. And then we can compute this coefficient, C, and C goes to 1 when we have a noisy signal, and it goes to 0 when we have a tonal signal. So here you can see R is the prediction residual amplitude of the spectral line in time and frequency, R, T, and F. And here we have the phase of the spectral line in time and frequency, and the predicted values are hat K for amplitude and phi hat K for phase. So here we try to compute or predict the spectral lines and the phases. And the more predictable a signal becomes, the more tonal it is. Because when you have a noise-like signal, the noise signal is totally random, so there's nothing to predict. So this is how you can imagine it. When you have a noisy signal, there's nothing to predict, and this is how you can recognize a noisy signal, as opposed to a tonal signal, which you can predict. Yeah, another important property here was the spreading function, which tells you how the sensitivity of the neighboring subbands changes when you have a tone at a certain frequency. Right. So you should have also seen this when you looked at the psychoacoustics. Right? Remember the spreading function and frequency? So here's the frequency scale, right, F, and here we have a tone, which appears as a peak in frequency at this given frequency. Right? So when you have a tone, then you can imagine that the ear is busy with this tone, and if you have another weaker tone at the same frequency, then it's hard to hear if there's another weak tone, right? Because the ear is already kind of saturated with this tone. And this is shown here with the simultaneous masking. So the tone goes up to where we have this dot. So here, the tone amplitude goes up to here. Right? And in order to hear another tone at the same frequency, it needs to be above this threshold. This is called simultaneous masking. So if we have a tone at this strength here, we just can't hear it. But if the tone is a little stronger, then we can detect it, then we can hear it. Make sense?
Yeah, so this peak is a masker, right?
Yeah, so this is masking. This is not a masker, but if you have a mask, well, this is the masker, dot, and this is the masking threshold.
And masking is another peak which is under this spreading function.
Yeah, so it could be something down here, and this is masked by the masker.
And why is it called critical band? Is it how is it related? Mask and critical band.
Critical band shows you the width of the Barbed band, which is here. Okay. So here you can see this is lower and this is upper. So imagine these dashed lines show you the Barbed band in this vicinity. Right. That's why it's called a critical band. And this is a critical band because the scale here is the Barbed scale. So this is the non-uniform frequency scale given by Barbed bands.
Kind of logarithmic here. Can we call Barbed scale kind of logarithmic?
Sort of, yeah. So the Barbed scale, as we saw, becomes wider towards higher frequencies. Right? Like a logarithmic curve, right? When you go to higher values, it rises more slowly. So if you want to rise by a certain difference, then you have to give the x values larger differences. So here we have uniform Barbed bands. On this scale, Barbed bands have all the same width. Right? But that also means that the same width here would be 100 Hertz, and the same width here would be 3.5 kilohertz. As we just saw. Yeah. Makes sense? And when we are in this Barbed scale, then those the masking threshold for neighboring frequencies can be approximated by those straight lines. Right. So we saw when we have a mask key, a signal which is masked, it can go up to this level before it becomes audible. So here at this point, the mask key becomes audible. Yeah.
With regards to simultaneous masking, if it becomes audible at that particular frequency, there's no change in quality, right? Because we already had a tone signal at that point. Now you're saying that if you raise it above a certain loudness, we are able to hear it. But there's no difference in quality.
It's what?
There's no difference in quality in that.
Exactly.
Right, but then like, what's the significance of simultaneous masking? Because the only difference is loudness.
Yes.
So the overall thing would be it's just louder. There's no difference in the quality.
Right. Exactly. You're right. That's all. Right. So that means here, when you have simultaneous masking, you are able to detect a change in the loudness.
Loudness.
And that's all. Right. That's simultaneous masking. And since ear has only so much ability to detect a change in loudness, this is what determines the simultaneous masking. Right?
Excuse me, Professor, why do we call it simultaneous masking?
Because it's on the same frequency. Simultaneously on the same frequency.
With the tone.
Yeah. So you have a strong tone and you have a weak tone at the same frequency. So simultaneously at the same frequency. At the same time, at the same frequency.
And right now we have only one tone here, we have the strong one, not the weak one. Right?
Yeah, so what we see here is the threshold. And the threshold tells us how strong a tone must be before we can hear it.
This band.
Yeah, or in general, also in the neighboring frequencies. You have a neighboring frequency?
We see that this pure tone or masker is it going to affect the neighboring frequencies. But why are we introducing this critical band in this phenomenon?
Because in this critical band, in this Barbed scale, these the spreading function has this nice straight slopes, right? So it's becoming straight. So you can say you have so and so many dBs per bar. So again, it's simple to model. That's why you go to the Barbed scale here. Another question?
Yes. So for us, is it true that it doesn't matter if we have one high peak or two peaks on the same frequency, like lower one and higher one? They will just add up, on one will mask another.
You mean if you have two mask keys? Or what do you mean?
Yes, like we have this median frequency with a peak, right?
Yeah.
Here. And if there will be another signal, another tone on the same frequency but
Yeah.
lower in amplitude, will these two tones add up, or one will just mask another?
Well, actually, depends on the phase. If they are in phase, they will add up. If they are in opposite phase, they will actually reduce. In each case, they change the loudness. And the ear is able to detect this change in loudness if the mask key is above this threshold here. It doesn't even say if it's stronger or weaker. The ear can detect it. That's the point.
So, for example, if we have another tone with this frequency but in opposite phase, this masker can one can be minused by another, so we cannot hear anything.
But it depends on the strength. So anything which is below this level here becomes inaudible. So if you have anything weaker than this, then the ear cannot detect it. It's not audible to the ear that there is something because of the limited sensitivity of the ear.
Below the graph of spreading function on the just that point.
Yeah.
Which one?
Well, we're still talking about simultaneous masking, right?
No, I'm asking below the spreading function graph or the simultaneous masking.
Yeah, what about it?
I mean, when it will be inaudible, below the spreading function or the simultaneous masking?
Yeah, everything below these curves. So this curve here is the spreading function, and anything below the spreading function is inaudible. So this is actually why I wanted to come next to. So when we have a sinusoid which is slightly next in frequency, so not on the same frequency but slightly nearby, then it becomes more easy for the ear to detect something. So this now gives us a newer quality, right? And this new quality makes it easier to hear for the ear, right? So you can imagine when you have something very close by, then this results in a beating going up and down. And the further away we come, the faster this beating becomes. Right? And this is something that the ear can more easily pick up. And that's why the threshold goes down, as you can see here. So it actually goes down to both sides, but actually to lower frequencies it goes down more quickly, because it turns out that inner ear filters have a more steep slope towards low frequencies than towards high frequencies. So those inner ear filters are non-symmetric. And that's why also this masking threshold is non-symmetric. So that's why you have this more steep decline. So which means that the ear is becoming more sensitive more quickly when you go to lower frequencies than to higher frequencies. Right. And after some point, so it actually turns out when you're roughly reaching this boundary of the critical band, then it doesn't sound like beating, but it sounds more like two tones. Right. So there's at some point some transition where it sounds more like two tones instead of one beating tone.
And one more question, simultaneous masking is a dot or is it line?
What?
On
Again?
this graph.
Again?
On this graph, simultaneous masking is 1 point or line?
Line.
I don't understand the difference. What do you mean with point or line? You have sinusoids. Sinusoids are neither a point nor a line.
Set of point.
So this point here represents a sinusoid with this strength at this frequency. Right? And simultaneous masking means anything that is masked by the sinusoid. So you have a mask key which is on the same frequency below the masking threshold. So this is the effect. Right? So the effect that a strong sinusoid can mask a weaker sinusoid is called simultaneous masking. Make sense? And yeah, so this can be seen as basically this line if you want to say it's a line, then you would say everything that lies on this line here below the top here is masked, and this represents the simultaneous masking. Yeah. And what's also important is that it depends on the strength of the masker. So if this dot, if the strength here of our sinusoid goes down, then the mask goes down with it. Right? So there's in dB is always this distance here. Right? There's a certain distance from the strength, the loudness of the sinusoid to the top of this spreading function. And this is called the time simultaneous masking threshold. Right? So here, this threshold here is called simultaneous masking threshold. So that's basically this point here. Maybe I should call this threshold. Is this where the question came from the slide here? Yeah, so here you can see the sound pressure level here is in dB for the power. Right? 10 times log base 10. So basically, the vertical axis is a logarithmic axis, and the frequency axis is kind of a logarithmic axis. Not exactly logarithmic, but similar. Yeah.
One question actually from your book.
Mm-hmm.
There was, when we tried to understand the psycho-acoustic model and we tried to quantify this further in the next step, so we take the analysis filter result and we divide it by the delta, but the delta is masking threshold times 2. And the masking threshold is all computed in the frequency domain.
Yeah.
The analysis filter result is in the time domain. This was a bit...
So why is the analysis filter output?
It is partially because it has its spectral resolution because it has subbands.
Yeah.
So that way it is in a way it is in a frequency, some sort of frequency domain.
Right.
But it was not totally clear. Could you please expand a bit on that? I mean,
Yeah.
on how we exploit this to further quantize because we take the analysis filter result, we divide it by this quantization step size to obtain our output at the encoder. So, if you could expand a bit on this.
Yeah, so how did we call the output of our filter? It's not frequency, it's not time, but time frequency, right? So we have frequency, which is the subband index, and we have time, which is the block index n. So, let's just say, this is frequency. Here it's in the bar scale, so we need to go back from the bar scale to the linear scale to apply it. And when we're in the linear scale, then we apply those different quantization step sizes which we obtain from this to the different subbands along the index for the subbands. So we apply frequency to frequency. Right? We just have to compute which subband belongs to which bar scale. Right? So it fits. This is frequency, and for each block n with index n, we have a frequency representation. So we apply this quantization one block after the other, but remember, from one block to the other, we might have different signals. So basically, we need to recompute this masking threshold for each block of our signal. Make sense?
Yes.
So remember, when we have our filter bank, we subdivide our signal into blocks of 1024, and each block of 1024 audio samples gives you one block of subband samples. Right? And then the index lowercase m is the block index. So for each block, we get a spectrum in the subbands. But if we vary m, lowercase m, we have a time signal. So for each subband we have a time signal with m, but we also have the spectrum with k. And that's why it's time frequency. Make sense? So this is something you need to keep in mind, that after the filter band we have both. We have frequency and time. We have frequency and the lower resolution in time. Yeah, and basically for every block we have to compute the masking threshold according to the sinusoids that we see in it. Right? So in each block we have different sinusoids, and for each sinusoid we need to apply the spreading function. Make sense? So this is basically really at the heart of our psychoacoustic model, this spreading function. Many of those spreading functions make up our masking threshold of our signal. Yeah?
Since we can see that in each particular subband, the slope of this masking or spreading function is not the same. For example, for higher is lower, and for lower frequencies slope is higher. So what do? We make it average when we represent a mask within each subband.
Basically, for each subband you have to see if there's a sinusoid, right? And then for each sinusoid you have to compute this spreading function. And the spreading function spreads over all the neighboring subbands. Right? So for each subband you have a spread over the neighboring subbands. And then you add them all up. And this adding up is actually also something of an art which we come to next. Right? So you cannot simply add them up, but you have to do something special. Yeah, so maybe I should come to the next set of slides. Or the next slide. Right, so here you can now see our spreading function in numbers, basically. So here the first formula gives you the simultaneous masking, and you can see the simultaneous masking has this alpha, and this alpha is the tonality index. So if alpha is 1, then we had a tone, right? And then we get a simultaneous masking of 14.5 plus I, and I is the index for the critical band. So here, this is the critical band index. So you can see actually the simultaneous masking is also dependent on the critical band. So basically, from the peak of the sinusoid to the beginning of our spreading function, we have 14.5 dB plus I as the Barbed index. For instance, if you're in Barbed band number 10, then you would have 24.5 dB simultaneous masking. Right, so this is the peak of your spreading function. Yeah. So here again, you have a noise coefficient here. So here the first is alpha, and then you also have this alpha nu, which is some noise coefficient, which is also kind of a tricky function, which is usually what I neglect in my models. It's too complicated, right? And this is also something that you need to get a feeling for. What's actually relevant for the model? Right? For instance, in the model I will show you, I set the I to a fixed value because otherwise it's becoming too complicated. And it also turns out it doesn't really matter so much. Right? So basically, making a psychoacoustic model is part science and part art, where you try out how it works. Right? You fiddle in with different coefficients, and then you listen to the result and see how it, or hear how it sounds. Because it depends a lot on your system, what kind of bitrate you have, what kind of subband decomposition. So there are so many other influences which are stronger than the fine detail of this model here, that you actually have to try it. And that's also why we gave you one of the seminar assignments to fine-tune a psychoacoustic model, because part of it is really art. Changing things, simplifying things, and listen to them. And then take the combination which sounds the best. So yeah, as I mentioned, usually I set the I to a fixed value, so that I neglect the changes across frequency. I neglect also this alpha nu, which I set to, basically, then I have just two states, noisy or tonal. Yeah, so this is the case for alpha equal 1 for the tonal case, and this basically disappears. Yeah, and then basically we have a difference for tonal. You have something like 20 dB simultaneous masking, and for noise you have 5.5 dB simultaneous masking. So if the tone is not really a tone but narrowband noise, then you can imagine that the ear becomes less sensitive, because then it's even more difficult to pick up something, right? Like detecting changes in amplitude for a noise is much more difficult than detecting changes in amplitude for a sinusoid. Right. Yeah, does that make sense so far? So again, formulas for the approximation. So here you can now see the numbers in the picture. So here's the case for noise. So we have 5.5 dB noise masking. And here in the lower branch you have 27 dB per bark, and the upper branch you have this 14.5. Isn't shown here. Yeah, so you have those two different slopes. Here you can see the slope for the steeper one going towards the lower frequencies. Yeah, we can actually try it here with this little Python script which I wrote. We have two tones. It generates two tones at different levels. So the first two arguments give the frequency of those two tones, and here you can see the level of those two tones. And then you can try to adjust this level until it becomes audible. Right? So maybe you can try it. So maybe for just a tone, my built-in speaker might be sufficient. Yeah, this is also something you should try at home, because this Python script is also in 2, and you can easily execute it on your own laptop, and then try different combinations of frequency and amplitude. So here I'm opening it. In my editor, and you can see it's really a small program using my sound library here. Sound, you can find sound.py also in Moodle, which gives you an easy interface to generate tones. So here first it reads in the 4 arguments, turns them into floats. Right, in the first line here, when you call it from a terminal shell, in the terminal shell you can give it arguments. That's also why it's important to call it in the terminal shell, not by double-clicking. That doesn't work. In the terminal shell you can give it arguments. In a Linux terminal shell, you should always, again, everybody should have Linux, right? And then you open a terminal in Linux using Alt-Control-T. If you're not having Linux, you should install it now using dual boot or VirtualBox. Dual boot is actually much easier. Right. Otherwise, if you don't have Linux, it doesn't really work. Yeah, so if you don't have Linux, you cannot be successful in this course. Right? So really everybody should have it. Yeah, and then here it generates 1 second. X is the time axis, and it uses 48,000 samples, and 48,000 samples per second is my sampling rate, so this is actually 1 second. And then here I'm computing the sinusoid on this X vector, by multiplying 2 pi with x, and then the frequency in hertz. So this is a number of cycles per second, plus the same for another sinusoid. And I multiply each by the corresponding levels. And then after adding them, I play back to the sound card. Does it make sense? So everybody should be able to understand each line of this program. If you don't understand each line, then you should ask me. If there's one line you don't understand. Do you understand each line? Yeah?
Formula from 15th line. It's taken from slides?
No. It's not in the slides. It's so easy. It's obvious.
Just sinusoids.
Huh?
Just tones, just
Yeah.
2 sinusoids.
Yeah, just 2 sinusoids. So here have 2 sinusoids. Here's frequency 1, here's frequency 2, and they have different levels, level 1 and level 2. Right, so the level should be between 0 and 1 in order to avoid overload of the sound card. So the x basically goes from 0 to 1. Right? Here you can see lin space produces values that go from 0 up to 1 with 48,000 steps. Everybody familiar with lin space? So if you apply the sinusoid to 2 pi x, then you get 1 period. Right? Because x goes from 0 to 2 pi. Make sense? So if I drop this track 1, then I just have 2 pi x. And then we have just 1 period. Because sinusoid has 1 period over 2 pi. Remember, the sinusoid in Python is based on radians, and in radians 2 pi means 360 degrees. So if track 1 would be 2, then we have 2 periods. If it's 3, then we have 3 periods, and so on. Make sense? Or shall I explain more? Well, if everything is clear, then I can let it run. Yeah, so if anything is not clear, take the advantage of it and ask me. That's what I'm here for. So, let's see. Python 2. It's already maximum loudness. Let's try my speaker here.
Bluetooth mode.
It's not really working. No. Okay, my speaker is not really working, so let's try again with my built-in speakers here. So you have to be quiet in order to hear it. Oh. No, nothing is working. Sorry about that.
mode.
Not working. Yeah, sorry. I guess you have to try it at home. Somehow my internal speaker stopped working and the external speaker is also not working. So, demo effect. Yeah, so here you can easily test how strong the mask key needs to be before you can hear it. Right? Just increase it slowly or decrease it slowly until you cannot hear it anymore. And also try it at different frequency distances from this masker. Right? So here we have a masker at 440 Hz with amplitude 1, and then we have a mask key here 40 Hz away, 40 Hz above, with amplitude 0.05, so much weaker. And you can try out at different distances, frequency distances, how high you can go before you can hear it. Right? And you should notice the closer this frequency comes to this 440 Hz, the stronger you can make it before you can hear it. Right? And this basically comes from this slope here. And the closer you come, the higher this masking threshold becomes.
Excuse me, sir?
Yeah.
Are we supposed to hear only one tone when it goes above the threshold, or two tones at the same time?
Yeah, when you are below the threshold, you should only hear the 440 Hz tone,
Okay.
the masker, because the other one, the mask key, is masked.
Okay.
Right? When it's masked, it's inaudible. So when you hear two tones, then you know it's above this threshold. Right? So if this other sound here is, say, in this strength here, you can hear it either as beating or as two tones.
So is it quite distinguishable when it goes above the threshold?
Yeah. Only when it's above the threshold you can detect a change. If it's below this threshold, you can only hear this 440 Hz tone. Right? And that's basically what we built it for. We want to have a coder and decoder such that the decoder plays back the music and it sounds exactly the same as the original. Right? That's our goal. So we want to hide something below this masking threshold, our quantization noise. Yeah. So we have quantization noise, but it's inaudible. That's the point of code. We don't want to change the audibility. I mean, we don't want to change the sound. The sound needs to be the same. And using these tools, we can achieve it. Yeah, so now the case of two sinusoids. Right, so here you can see two sinusoids, and each has a spreading function. Right, here you can see a weaker tone, so the spreading function is accordingly lower. And at some point, those spreading functions intersect. Right, so here you can see it. And then basically, you take the dominating masking threshold. So if you have two masking thresholds intersect, then basically you take the stronger ones for the superposition. You have both.
Inaudible.
Right. Yeah. So again here, this is one critical band. Yeah, and also this shows when you have quantization noise, in a critical band, basically you add up this quantization noise to become one signal. Right? So this is relevant when we have several of our subbands covering one critical band. Then we take the power of all those subbands, add them up into one for one critical band, because then we apply those spreading functions in the critical band domain. Yeah, so the common way to superimpose neighboring spreading functions is to just take the maximum. Yeah, and here you can also see the two different slopes. So the lower, steeper slope is this 27 dB per bar. And this upper, not so steep slope is, here in this case, 24 plus 0.23 divided by the frequency in kilohertz, minus 0.2 loudness in dB. And this gives you a dB number per bar. So this is then the slope. Again, a kind of complicated formula for the upper slope. So what I usually do is I make some assumptions here for the frequency and the loudness and keep them constant. That makes the implementation easier. And this is also what I did in the upcoming examples. Yeah. Does it make sense? So you see, strictly speaking, the slope changes depending on the loudness and the frequency. Yeah, and I find this nonlinear superposition very convenient because in this case we don't need tonality. So very convenient. So this actually comes out of a model which is described in the paper by Frank Baumgartner and co, which you can download here. And this is based again on this paper from Lutfi, a power law transformation prediction masking by sounds with complex spectrum, from the Journal of the Acoustic Society of America back in 1985. And they propose a superposition like this. So here you can see a sum. I is the different spreading functions. So here I is the intensity of the case spreading function, where the intensity here is acting like a power. And then we have a suitable parameter A, for which we can do this superposition. So we have this exponent A. We sum all those spreading functions with this exponent, and then finally we take the eighth root. So we exponentiate with 1 over A. So this is kind of a nonlinear superposition. So you can also think of, instead of a power, we sum up something else depending on this exponent. So for instance, A equals 0.3 is similar to a square root. So you could think this is kind of like a voltage, because the voltage is the square root of the power. But not exactly, because it's 0.3. Does it make sense? So basically we take the sum in a different domain. And this domain is given by this exponentiation. And it turns out this actually works. It's again an approximation of the observation from here. So this formula is not derived, but it's again a fit to the observation. Yeah, so we have a Python example here which shows the nonlinear superposition with parameter 2 alpha, 2r, 2a is alpha equals 0.6 in the bar scale. So this 2 comes from squaring our voltage. So power is voltage square, and then we have this a. So we have 2 times a in the voltage domain. So you can see 0.6. If it would be 0.5, then would it be exactly at 1. But here we are at 0.6. So for the voltage, we just need to exponentiate with 0.6. Make sense? So voltage square is power. Still remember? Voltage square is power. Like voltage square divided by R is power, right? So if you say R equals 1, then voltage square is proportional to power. Yeah, so this is our function which does the spreading function computation. Here I highlighted the most important parts. So here I have the spreading function in Barbed and dB. Here 0 going 0 to n fills. N fills is the number of subbands in the Barbed domain here. You can see here in the beginning. I give a definition here. N fills, number of subbands in the Barbed domain. For instance, 64. You just need to choose a reasonable number. So basically we subdivide the Barbed domain into a finer scale. Instead of having just 24 subbands, I'm now going up to 64 to get a finer frequency resolution. And we don't have to stick with full Barbed bands, we can go to fractional Barbed bands. And this is actually also quite common in audio coding. For instance, AAC and MP3 usually have half Barbed or third band or quarter Barbed band resolution. Yeah, here I have my simultaneous masking. So here you can see 14.5 plus 12. So this corresponds to Barbed band number 12. Right, remember this formula? 14.5 dB plus I. This is this one. Then here the upper slope. FDB 7.5, so here I also just assume a certain frequency, I think a kilohertz to get to the 7.5. This is the 26 dB for the lower slope, so this is constant as we saw. Yeah. Does it make sense? These numbers here? So we can go back. Here, for instance, here we have a level in dB, 0.2, and here we have plus 23 F in kilohertz. So if F is 1 kilohertz, then we would have 24 plus 0.23, 24 plus 24.23, and then here minus, say, what did I take? 40 dB maybe? What happens if we set it, we use 40 dB? So 40 dB, 0.2 times 40, yeah?
Yeah, I have a question with the quantization noise. So what if the quantization noise is above the masking system?
Then you can hear it.
How do we remove it?
You cannot remove it after you can hear it. It's impossible. It needs to stay below the masking threshold.
Okay.
Yeah.
But then we have the step size of the data, right, and not the number of bits. So
the step size delta needs to be small enough so that the resulting quantization error stays below the masking threshold for each frequency and at each time instance.
and then how do we relate to the number of bits? Because in the mid-rate quantization, we use the number of bits to calculate the step size, and here we don't use it. We use
Yeah.
the data which has been
So
calculated.
here you compute the step size, and from the step size you would compute the necessary number of bits. So the other way around.
So is it with the maximum value of the delta? We calculate the number of bits?
No, you have, see here, for each frequency you have a threshold, right? Or here, right? After you did the superposition of all the sinusoids, you get the total threshold, IT. Right? So this goes up and down in the spectrum for each block, for each frame. And you need to make sure that all the quantization noise is below the threshold. And you do this by computing the threshold which generates noise which is below the threshold. Right? So given the maximum noise, you can compute the maximum quantization quantization step size. From the noise, you come to the quantization step size, and then from the quantization step size, you can compute the necessary number of bits for this frequency bin at this block. So for each block, you need a different number of bits. So you have variable bit rate.
So do I need to do the superposition of the masking threshold as well in each block?
Yeah, so this goes over all the sinusoids. Right? So basically for each sinusoid you need to compute this masking threshold, this spreading function. And then you will superimpose all of them according to this formula here. And then you get a total threshold. Right? So this is basically what I do here, the superposition. So, yeah, here this FBDB 7.5 you basically obtain by plugging in some dB number here. Right? So for instance, if you have 40 dB, 0.2 times 40 is how much? 8, I guess, right?
Right.
Yeah. So you would have 24 minus 8, and then you're at 16. Right? So maybe it's a little bit more. Maybe you have 60 dB. 60 dB times 0.2 would be 12, I guess. Right? 24 minus 12 is 12. Yeah, something like that. So here's a number, and this number, this is actually also something you can play with. Right? You can take here, you can see these numbers, they contain assumptions about frequency and about the signal strengths. And the signal strengths, again, depends on how loud you listen to the result. Right? If you turn up the volume, then this loudness becomes higher. So actually, this value here, the 7.5, depends a lot on how loud you listen to it. Questions? Does it make sense? So those first lines should be clear to you now. Are they? Okay. So this is basically how I define my spreading function. And then I'm constructing it here using an array containing one triangular function. This triangular spreading function. So here you can see, here's the FBDB 7.5 here for the lower slope. And then here minus 2.5, this is the simultaneous masking, I think. Yeah. Here's the simultaneous masking. No. Where's the simultaneous masking? Yeah, it is simultaneous masking here. And here I have some correction factor. And here it goes up, it uses n fills number of samples. So basically this is one prototype of our spreading function which I'm constructing here, which I then shift on top of each sinusoid that I have in the signal. Yeah, so here, this is the upper slope, and here's the lower slope. Here you can see the lower slope. And here convert from dB to voltage, and already include the alpha exponent here. So here I take the spreading function and turn it back into voltage using the exponent here and division by 20. And I already include this alpha for the summation. Right, and the summation comes in the next step. Here I'm doing computing a spreading function matrix, which I then use for the summation. So here basically I have a matrix, and each column contains the spreading function, and the spreading function is slightly shifted for each k. And k is basically our frequency index. So this k is the frequency index for our subbands in the Barbed domain. So each column now contains a slightly shifted spreading function. Make sense?
Yeah, and overall, this all spreading functions, they are not fixed. They really depend on the audible environment.
Yeah, right.
And of ear, certain ear.
Yeah. So here basically I have shifted prototypes in this matrix, and these prototypes are now multiplied by the loudness of our sinusoids at each Barbed subband. So I basically can compute our superposition now by just multiplying it with this matrix. That's the next step. So again, avoiding a for loop then for the computation. Yeah, so here the application of the spreading function is then simple matrix multiplication, which avoids the for loop in the Barbed domain, as you can see here. So here you can see it. I have mx bar. So this is the signal, the magnitude of the signal in the Barbed domain, exponentiated with alpha, like in our nonlinear superposition, and multiplied here with our spreading function matrix. Remember, the spreading function matrix had in each column shifted spreading functions. And here we have now a vector which is a column. Right? So this is a column vector. And that means the low frequency bin here is multiplying the first column with its magnitude, and the second entry computes the second column with its magnitude, and so on, and finally they all summed up. So then as a result we have the weighted summation of all the shifted spreading functions. Weighted and exponentiated with this alpha. So basically what we have then is this piece here, the summation piece. Right. So here the ITK is my matrix. Right. And then it also includes the magnitude of our sinusoids. So this summation here is our matrix multiplication. Yeah, so this is basically this here. And then finally we do our exponentiation with 1 over alpha. And then here, this vector here, mt bar, contains our threshold for this block in the Barbed domain. So this contains our threshold now in the Barbed domain. Make sense? So this is basically now the main part of our model. This empty bar now contains our masking threshold in the Barbed domain. So here returns the masking threshold as voltage in the Barbed scale. So basically this now tells us how much noise we are allowed to add for each Barbed band. So this already gives us the quantization step size. So basically each entry here tells us how much noise we can add, and we know how to compute the noise from the quantization step size. Still remember? What's the quantization noise power of a given step size, delta?
Square by 12.
Exactly. So the quantization noise power is delta squared divided by 12. So then you can compute it back into a voltage. Then you have delta divided by square root of 12. Right? So basically you just need to adjust it by the square root of 12, and then this is the quantization step size. So up to a factor, correction factor, we already have the quantization step size here in this vector.
Excuse me, but this is in Barbed domain, not in frequency.
Yes, exactly.
So we calculate the noise power in the Barbed domain.
Yeah, so now we have to go back from the Barbed domain into the linear domain of our filter bank, so that we know which Barbed band belongs to which subband. So that's the final missing piece. Right. Yeah, first we can take a look at an example here. Again here I'm taking alpha 0.6, the number of filters in the Barbed domain is 64, the number of subbands. Sampling frequency 32 kilohertz. And then I'm simply computing this matrix, spreading function matrix, using this function here. And this function just wants to have the maximum frequency, the number of filters, and the alpha. And then it plots this spreading function matrix as an image. So I'm using imshow to plot it. And here you can see the result. So you can see this matrix is 64 by 64. Right? 64 bands in, 64 bands out, because it's doing this multiplication and addition. And here these colorful lines are the shifted spreading functions. So each column is a spreading function here. Right? And you can see here, this is the center, and then you have a steep decay. And here you have the slow decay. And yeah, it's the other way around, because you have, let's see, when you multiply from the left-hand side with the subbands, then you have, yeah, basically comes from the convolution, right? You have the shifted version of your triangles on the center of each of the sinusoids, and that in effect is you convolve it with a reversed version. And this is why you have the reversal here. Yeah, does it make sense?
Yes.
So this is simply a trick to avoid a for loop here. And this makes it much faster in an implementation. Yeah. So here, this nonlinear superposition has the advantage that we don't need any tonality estimation, which is nice because the tonality estimation is kind of tricky. Yeah. And yeah, usually our signal from the filter bank is like a voltage, not like a power. We obtain a power if we square our signal, and hence our exponent is multiplied by this factor of 2, and hence we get 0.6 instead of 0.3. Yeah, and the frequency index is on the Barbed scale, as we saw. Hence we need a mapping from Hertz to Barbed in the beginning, from our linear filter bank scale to the Barbed scale where we apply the masking, and then we need an inverse mapping from Barbed back to Hertz to apply our found masking threshold to the quantization step sizes of our linearly spaced subbands. Right, so this is the final missing step that we now need. Yeah, and there are several approximations of the Barbed scale for this mapping, forwards and backwards. And an example can be seen here in this link from Stanford, an overview. So it's actually interesting to compare the different approximations from Barbed to linear and back. And the approximation we previously saw is from Zwicker and Turhart in 1980, analytical expressions for critical band rate and critical bandwidth as a function of frequency. Also in Wikipedia. And in Python, this approximation can be written like this. We have those arctangents functions which we saw before. But it only has an approximate closed form inverse formula. So from there we can go from linear to Barbed, which is quite precise, but we cannot really inverted. And that's a problem for our model, because we need to go back. So here's an approximation of the inverse. And you can actually test it. So we have a forward function and approximation of the inverse. And if we both apply one after the other, it should be identity. Right? We can simply test it using those scripts. So here is the forward function. We go from frequency in hertz to frequency in bar, the Z. Right? And you can see here we have sort of this logarithmic shape. Right? So at least here in the beginning it's linear, but then it becomes more logarithmic. And then we can test the inverse using this formula which we just saw. So basically apply this function to the output of the first, and then we get this. So here we can see the green is the identity, this is what we would need, and the blue is what we obtain. And then actually you can see we have quite some deviation here of, well, it's easily 1000 Hertz deviation, right? So this is basically making it unusable for audio coding. Too many deviations, too big deviations. So that's why we have to look for something else. We want to have something which has an exact inverse in order to avoid those shifting of frequencies. Yeah, and here we have another one from Traunmüller from 1990. And it's actually quite a simple formula for the Fourier transform. You can see it in the beginning, and then it has the exact inverse, which you can see here. And we can plot it. First there's another one from Schröder. So it even has a simpler approximation for the Barbed scale using this arc sine hyperbolicus. And then it also has an exact inverse, this one here. So two different approximations, each have exact inverses. And you can plot them and then compare them with our Barbed table, right, at a few points, which are plotted here. And then plot those different approximations, here going to the Barbed scale and compare it with our points from the Barbed table. And this is what we get. So we see the original Zwicker one is the red one. The red dots are from the table, and you can see Zwicker quite exactly fits to the table. Then we have the Traunmüller approximation, which is the blue one. It's not quite as exact as the Zwicker approximation. Here you can see a deviation here in the higher frequencies, the blue line. And then you see the green line is the Schröder one, which is better at high frequencies but not so good at the medium frequencies, which you can see by the deviation from the red points. Does it make sense? So this shows you the quality of the different approximations. So Zwicker is the most precise but not invertible, so that gives us an error. Then Traunmüller is not quite as exact, but gives us the exact inverse. Schröder is even less exact, but again gives us the exact inverse. Right. Yeah, so this is what I just mentioned. So Schröder is the least accurate, but it has the simplest, but it's the simplest, it has an exact inverse in closed form. And actually that is why it's used most often, and that's also why we use it. And it turns out the exact approximation to the Barbed scale is not so important, but what's really important is that it has the exact inverse. Right. So here's then our resulting conversion from Hertz to Barbed. This is simply this formula here, pretty convenient. And the next one is from Barbed back to Hertz. Again, a really simple function here. Right. And it allows us to have the exact inverse. Right. So this is then doing our mapping to Barbed. But I guess we can continue there next time because our time is up. Yeah. So thanks for your attention and have a nice evening.